Hello everyone. We're going to explore the inside of our planet tonight. Like in the travels we made in space or underwater, we will slowly descend to the Earth's core and we will discover what lays under our feet. To begin with, we will talk about various phenomena happening on the surface, like continental drift or volcanism. And then we will explore the various layers that exist between us and the center of our planet. As always, we will keep things very easy to understand, even if you have no scientific background at all. I will explain how the Earth's core shields us from solar radiation, how the Earth is progressively cooling down, and also how men have imagined or theorized what our planet was made of across various civilizations and along the centuries. Our ancestors were very creative. They envisioned different possible shapes for the world, flat, hollow, with passages to various underworlds. And we will also explore how they appeared, these visions, and sometimes how they survived in popular culture, in novels, in fiction. If you wish to navigate this story, you will find timestamps in the first comment. But for now, you just need to get ready for our journey. Sit down or lay down comfortably. Don't hesitate to close your eyes if you feel like it, as the visuals are not necessary to follow along. If you wish to keep this video or the audio to have them accessible offline, you can download them from my Patreon page. There is a link in the description. The soft music you hear is now going to recede and disappear. But it will be back at the end of our exploration journey to lull you to sleep and accompany you in your dreams about the wonders of our planet. We have a lot to discover tonight, so keep your mind open and peaceful. Our descent begins right now. We're going to begin our story in Russia, more precisely in the Kola Peninsula, near Finland. Why there? Because over a period of more than 20 years, the Soviet Union drilled in this region the deepest vertical hole ever in the Earth's crust, not to search for oil or another resource, but as a research and engineering project to study depth drilling, geophysical phenomena, and the nature of the rock layers. This hole is very narrow, only 23 centimeters wide, that's about 9 inches, but it's 12 kilometers deep, 7.5 miles, and to this day it remains the deepest artificial point on Earth, even though there are a few oil wells drilled in the past few years that are almost as deep. Now, 12 kilometers deep is just a little scratch for the planet. But at the scale of the Earth's crust, the solid rock layer we walk on, it is significant. In the Kola Peninsula, the crust is estimated to be 35 kilometers thick, 22 miles. At this depth, representing about a third of the crust, the temperature at the bottom of the hole is already 180 degrees Celsius, 350 Fahrenheit, and this high temperature made the drilling unfeasible, which is why it was stopped in 1992. The more we descend underground inside the Earth, the more the temperature rises. And this is just the beginning, because when we reach the core of our planet, we will find temperatures that are way higher, similar to the surface of the Sun. But why is the Earth so hot? To understand it, we need to go back several billion years in the past and look at how our planet was formed. According to current theories about the formation of the solar system, Earth and all planets orbiting the Sun appeared in the early ages of the system. The star system appears when a large quantity of matter gathers and starts accreting because of the gravitation. An accretion disk made of dust and gas takes shape, and progressively, over millions and millions of years, it gives birth to one or several stars at the center. In the case of the solar system, most of the matter went into the formation of the Sun, about 99% of it. The rest stayed in orbit around the Sun and formed planets and other smaller bodies. Two main kinds of planets appeared in the solar system: gas planets like Jupiter or Saturn, which probably have a solid core but are mainly made of gas, hydrogen for the most part, and this gas is kept together by gravitation. And there are rocky planets that are solid and have a well-defined surface. There are 4 of them in the solar system. Earth is the biggest one, and there are also Venus, Mars, and Mercury. And there are many more smaller bodies too, that are not considered planets because they are not as big, but they have a similar history. Dwarf planets like Pluto or Ceres, satellites like the Moon, and millions of smaller asteroids. Rocky planets appeared by absorbing most of the matter on their orbit. They cleared space of matter, bit by bit, after tens of millions of years of collisions with bigger and bigger asteroids, as the dust progressively concentrated in the solar system. In the case of Earth, it is believed that 2 protoplanets formed on a similar orbit. They finally collided in a very violent shock, and this is how the Earth almost reached its current mass. But in the shock, a lot of matter was ejected into space, and this matter would have formed the Moon. Above a certain mass, rocky bodies take a round shape because of gravitation. There are plenty of asteroids that are not spherical because they are not big enough. There is not enough mass for gravitation to shape them round. So from the moment it appeared and it took shape, the Earth was intensely hot as a result of its formation. Bigger and bigger objects collided with it, and their speed, or their kinetic energy, to use the scientific term, turned into heat. And the Earth is hot also because a lot of heat keeps being produced inside by nuclear fission. The Earth contains radioactive materials like uranium, that it received during its formation. And long after the planet was formed, this material continued to fission and generate heat. In the case of Earth, it is estimated that about 20% of its internal heat comes from residual energy from the accretion process, all these collisions that formed the planet. But for the most part, the remaining 80% of its heat, it comes from radioactive elements that keep fissioning, like in a nuclear reactor. But over time, a rocky planet cools down, starting by its surface. Heat dissipates in space, and nuclear elements inside disappear bit by bit as they disintegrate. This process can last billions of years. It is very slow, but it is how the external layer progressively turns from liquid rock to a solid crust that tends to become thicker and thicker as the planet ages. For example, in the case of Earth, it is estimated that heat production inside the planet 3 billion years ago was twice what it now is. The formation story of the planet and the laws of physics also explain its internal structure. Once a planet is formed, the various elements it is made of tend to migrate within it, and together with different levels of pressure and heat, this creates a differentiation between various layers. Under the Earth's crust, we will discover different layers that have different characteristics, different composition, different elements, a different temperature. But as we are going from the surface towards the center, let's begin with the crust, this solid layer where life appeared and on which we live. The crust is not even everywhere. There are places deep under the ocean where it is only 6 kilometers thick, less than 4 miles, and other places like in mountain chains, for example, where it can be up to 50 kilometers, 30 miles thick. It is mainly rock. We will look at its composition later, but as anyone who has experienced an earthquake or seen a volcanic eruption knows, the crust is not perfectly still and stable. The main theory nowadays that explains the motion and activity of the crust on a global level is called plate tectonics. It has been accepted by the scientific community since the 1950s and 1960s, and little doubt remains that this is valid because it explains very well multiple phenomena, such as the presence of the same geologic layers on different continents or the presence of similar species. It also explains seismic activity, the formation of oceans and mountain chains, and what we know about the internal structure of the planet. What plate tectonics says is that even though the Earth's crust is mainly rigid, the crust and a small layer just under it are broken into different plates that can move. They move extremely slowly, generally by just inches every year. But when you multiply this by hundreds of millions of years, the face of the planet with the location of continents and oceans can change completely. Why do these plates move at all? Because there is motion underneath, in the inner layers of the planet that we will explore later. Another explanation to their move is the pull, also known as the tidal force, from the moon and the sun. It isn't clear and the subject of debate still how these various forces combine to put plates in motion. And where these plates meet, their thickness and relative motion determine the kind of boundary between them. One can slip under the other and push it up. This is how the formation of the Andes or the Himalayan Mountains are explained. In the case of the Andes, there is a medium-sized plate that is almost entirely underwater, the Nazca plate, that passes under the South American plate, and it compresses it on its western fringe, which makes and continues to make the Andes rise. In the Himalayan Mountains, it is the subduction of the Indian plate that lifts the Eurasian plate. All plates do not collide frontally. Depending on their motion, they can rub one another too, and they can also diverge. There are rifts where new material surfaces and pushes in opposite direction. The largest rift on Earth is the center of the Atlantic Ocean. Hundreds of million years ago, Europe, Africa, North and South America were all parts of the same landmass. A rift that later became the Atlantic Ocean opened and pushed these continents apart. Where the plates meet, the forces at play are enormous. Most of the time, nothing happens, and tension may accumulate inside the rocky layers. They don't move despite the push they are subject to. And suddenly, sometimes after years or even decades, this energy can be released at once. The plates move up to several meters relative to one another, and there's an earthquake. Depending on its depth, the type of rocks, the direction of the forces at play, it can be more or less destructive at the surface. But because the shock waves may travel inside the crust, a shake can happen theoretically anywhere. But the violent ones and the most frequent ones happen near the plate boundaries. If you live in the middle of a large continental plate, like east of the Rocky Mountains or east of the Andes, or in most of Europe, you are unlikely to experience a powerful earthquake. But if you are near a plate boundary, earthquakes and volcanic activity are much more common. The most active seismic and volcanic regions of the world are located all around the Pacific Ocean, in a vast region shaped like a horseshoe almost, around the east of Asia and the west of the Americas. About 3/4 of active volcanoes in the world, and by far the biggest earthquakes, happen in that region. Bit by bit, the Pacific Ocean is shrinking. It's very slow, only 1 inch per year. But even though it will take hundreds of millions of years, the Pacific's days are actually numbered, whereas the Atlantic Ocean is in expansion thanks to its rift. One day, Asia and America will collide, and they will form a single continent again, as they did in the past. There was a time when all the Earth's landmass formed one single continent, a continent called Pangea. It is believed that plate tectonics appeared only 3 to 3.5 billion years ago, when the Earth had cooled down enough for rigid plates to appear on its surface. As Earth keeps aging and gets colder, as it loses heat and produces less of it, because its stock of internal fissile material decreases, plate tectonics will also end one day. The crust will form one single thicker plate. Its surface will stop changing shape. It is believed that on other smaller planets, like Mars for example, this already happened. Like Earth, Mars has a differentiated structure, and it formed in a similar process of accretion, but it has already cooled down more. It is a smaller planet, and there would no longer be plate tectonics on Mars. A consequence of plate tectonics with new material appearing in rifts and older material melting again when it is subdued under a plate is that the material on the surface of the Earth is much younger than the planet itself. Oceanic floors are only 200 million years old in average, when the planet is several billion years old. The oldest layers of rock in the crust are about 3 billion years old, and they are found in continental regions in the middle of large plates like in Central Asia. In any case, looking at tectonic plates makes the map of Earth look very different. The largest plates are the Pacific Plate, that occupies a big part of the Pacific Ocean, the Eurasian Plate, that contains most of Asia and Europe, with the notable exception of India. There is the African Plate, too, the North American Plate. There are also much smaller plates like the Caribbean or Arabian ones. Now plate tectonics, the theory, is less than a century old, and before it, mankind came up with various and very different visions or explanations of natural phenomena like earthquakes, or more generally, what shape the Earth had and what it was made of. The majority of ancient civilizations, the ones that left documents at least, pictured the world as flat, which is logical because this is how we perceive it. For ancient Egyptians or Mesopotamians, the world was supposed to be a disk floating in the ocean, and the sky was a dome with the moon, the sun, and the stars embedded in it. Greek philosophers are generally credited for theorizing the round Earth, and they did, but among many other theories, some of them thought that the Earth was a short cylinder, or that it was a dish riding on air. In Europe, the ancient Norse and Germanic people also believed in a flat Earth, with the Earth surrounded by an ocean, and a central pillar or a world tree in the center. The same in China, too, except the Earth was pictured as square, whereas the heavens were round, and this assumption remained unquestioned for a very long time in China, until the 17th century, and the introduction of European astronomy in the country. In India, ancient texts picture the Earth as flattish, but this time as just one of a stack of flat disks, each of them being a different world. From the 5th or 4th centuries BC, the view that the Earth was round gained traction in ancient Greece and among Indian astronomers too. At the time of the Roman Empire, it had become a mainstream view, among scholars, because in fact the general population was not educated and probably didn't even wonder what shape the world could have. This vision remained into the early medieval period and was also adopted by Islamic scholars. There was a great development of astronomy and mathematics in the 8th and 9th centuries in the Middle East, and this allowed to calculate the movement of planets. Islamic scholars were aware that the sun rises at different times in various parts of the planet, and there was apparently no dissent among them to the round earth theory. Various Muslim scholars explained that the earth looked flat because it was so big that its curvature was not visible for one single person. That was a good explanation. But one point that remained hard to explain was how people living in the southern hemisphere didn't fall. There was no understanding of gravitation, or that what we call up and down is a product of our perception. What we call down is actually the direction towards the center of the earth, the direction of the gravitational force that keeps us stuck to the ground. And this issue remained pending for centuries. Contrary to what people suppose sometimes, in medieval Europe during the Middle Ages, the Earth was also seen as round, at least in universities and in official teachings. The vision enforced by the Church in particular was that the Earth was round, but also that it was at the center of the universe. And it is because of this debate, this conflict about the position of the Earth relative to the Sun especially, that some astronomers like Copernicus or Galileo were condemned by the Church because they insisted on putting the Sun at the center. Now common people may have assumed during this period that the Earth was flat, just out of their sensory experience, and even educated navigators were not perfectly comfortable with the round earth theory. For example, the Portuguese, who were the first European navigators to explore towards the south along the coasts of Africa in the 14th and 15th centuries, were nervous that the ocean may end and that their ships could fall into a void eventually. But finally they pushed even more to the south, and in the 1400s their navigation confirmed that the ocean never ended abruptly. In the 16th century, the first trip around the world was made by the Magellan expedition, and from this moment on, the various hypotheses of Earth being something other than round were mostly eliminated. Another vision that appeared long ago and lasted longer was the hypothesis that the Earth was round but hollow, or that it contained an interior space with an entirely different world. This concept of a subterranean land inside the Earth appeared in various mythologies. In Greece, there was an underworld where souls were supposed to go after death. There was an ambiguity in Greek mythology about where it was, whether it was a real place with an entrance from the physical world, or just another dimension only accessible to spirits. There were similar underground worlds in Norse mythology or in Tibetan Buddhism, and this is also the kind of representation of hell that existed in the Christian and Jewish traditions. In various mythologies, there were legends about the actual entrance to the underworld. For example, in Ireland, there is an archaeological site called Raskrohan. I guess it's pronounced Raskrohan in Irish. Sorry, my pronunciation is probably bad. Anyway, according to the legend, there was a cave on this site from which creatures from the underworld emerged. Also in Ireland, there is an island called Station Island, an ancient pilgrimage site where a cave supposedly communicated with the inside of Earth. There is a chapel built on the cave, and it would have been closed since the 17th century. There are many more examples of legends and traditions about an underworld in Hindu mythology, Native American legends, or in Russia about the Samoyeds. The Samoyeds are a Siberian tribe living north of Siberia in a very harsh environment. According to a Russian legend, the Samoyeds traveled to a cavern city to live inside the earth. Sometimes this underworld could be hell. It could be a refuge where people found a shelter or a new land, or it could be the place from which tribes or people came from. But in the 16th, 17th centuries, at the time when the round earth theory was replacing for good other visions of the world, the hollow earth hypothesis resisted in Europe, including on scientific grounds as an explanation of certain phenomena. One proponent of this idea was Edmund Halley, an English astronomer and an important and serious one. Halley's comet is named after him. He computed the comet's periodicity, among other works. At the end of the 17th century, he put forth the idea of Earth being like a hollow shell, with two inner concentric shells, and after all that, a core at the center. He supposed these different spheres had their own magnetic poles. I'll tell you about magnetism a bit later. And he also supposed that they rotated at different speeds. That could have been an explanation for anomalous compass readings, and maybe even for aurora borealis. He supposed that aurora borealis could be gas escaping from the space between our sphere and the one below. There were other tentative descriptions of the inside of Earth in the 18th and early 19th centuries, sometimes including an internal sun at the center of the Earth. Bit by bit, in the 19th century and early 20th century, these ideas exited scientific circles because the understanding of the Earth's mass, new hypotheses about the formation of planets, the better observation of other planets too, all of these made these descriptions of the hollow Earth and sometimes the people who would have lived under our feet little credible and completely unsubstantiated in any case, which meant they couldn't be a part of the scientific field. When it became possible to test the ground with seismic waves, when the theory of relativity better defined what gravitation was, or when holes were drilled several kilometers into the ground, like the Kola borehole where we started, the hollow Earth hypothesis died. It died as a scientific conjecture, But in the meantime, it had started a successful career in fiction. Already in 1741, in the 18th century, there was a novel of fiction by Ludvig Holberg, a Norwegian writer, about a character who fell through a cave and lived several years on a smaller globe inside the shell on which we live. This hollow earth appeared under one form or another in many more novels in the 19th century, including by high-profile and very successful writers like Edgar Allan Poe or Jules Verne. Maybe the most famous novel with another world inside the Earth is Journey to the Center of the Earth by Jules Verne. It describes a prehistoric subterranean world explored by an expedition that found a passage under a volcano in Iceland. The popularity of the concept in fiction has not decreased, and maybe it's because it has become really hard to imagine lost worlds on the surface of the planet after the world has been entirely explored and mapped. But under our feet, why not? It's a fun idea, at least. Apart from a hollow world with different spheres inside, like Russian dolls, another conjecture that looks even harder to believe but was actually clever when you think about it, was that we could live not on the outside of a ball or a sphere, but on the inside, and we would walk on its internal wall. In this vision, what we call space, the sun, planets, stars, would actually be inside the sphere. And this is clever because even though it doesn't work at all with what we know now about the distances, the size of the sun, or of the universe in general, it could explain many things back then. First, the fact that it never ends when you travel on Earth. There is no edge to it, and if this is not the outer surface of a sphere, then it has to be the inner surface. And also it could explain gravity through centrifugal force. If the sphere we live in is spinning, it is logical that we are stuck to the surface, that we have weight. It makes sense, after all. This is the solution that has been imagined to artificially recreate Earth-like gravity in space for astronauts, in case large spaceships are built one day. A module that spins and gives people weight through the centrifugal force. But knowledge of what lies under our feet, under a few miles of crust, really developed later in the 20th century, when models of the planet's formation appeared, and geology made giant leaps forward with new techniques like the use of waves that travel across layers of rock and can reveal what they are made of based on how fast and in which direction they propagate. So now that we have examined the first few miles at the surface, it's hard time to start our descent towards the core of the Earth. There is a boundary between the crust and the region underneath the mantle, and this boundary is called the moho. It's about 500 meters thick, and it is where the composition of the Earth changes. In the crust, the most abundant element is called silica, or silicon dioxide, what we generally call sand, because it is its main component. There is a profusion of different types of sands, but silicon dioxide makes 50 to 60% of the crust. Another major component, about 15% of the crust is aluminium oxide, alumina. And then there are plenty of different components, also oxidized: calcium, magnesium, iron. Oxidized means that basic elements like silicium, aluminium, or iron are associated with oxygen. Basic elements do not always come pure in nature. On a rocky planet like Earth, they have a high propensity to form molecules with oxygen. And actually, oxygen is probably more abundant than you could think on Earth. Looking at the entire planet now, not the crust only, it is estimated that oxygen represents about 30% of it, almost a third. The only element that is more abundant in the entire Earth is iron. Iron is about 32–33% of Earth. Out of these two, the other elements are silicium, about 15% of the planet, and magnesium, 14%. This makes the Earth very different in its composition from the rest of the solar system. It is not that different from other rocky planets, but the main components of the Sun and gas giants are hydrogen and helium, whereas these elements are marginal on Earth. They are not absent, neither. There is hydrogen everywhere there is water, but at the scale of the planet, hydrogen represents less than 1% of the total mass. The nature of the elements under the crust is very different from what we find in our biosphere at the very surface. And the reason why the planet is not homogeneous, the reason why its various layers are made of different elements, is this differentiation phenomenon I mentioned earlier. When rocky planets form, the heavier, the more massive elements tend to migrate towards the center, towards the core. For that reason, the Earth core is estimated to be made of 90% iron and 6% nickel, more massive elements. We will see later that this is very important for life on the entire planet. This differentiation happens on every rocky body of a sufficient size. The heat inside a planet maintains it liquid, so that materials that are denser than average tend to fall down to the center, whereas lighter elements migrate towards the surface. The differentiation never reaches 100%. This is why there is iron in the crust too, and it didn't entirely join the core. But as a rule, the more we are going to descend towards the center of the Earth, the more we will meet heavier elements such as metals. In the mantle that we are now entering, as we pass this boundary called moho, the boundary with the crust, the chemical composition suddenly changes under the crust. We're going to discover a completely different environment. The mantle makes 2/3 of the Earth's mass, and more than 80% of its volume. It is the bulk of our planet, if we think in geological terms. Just under the crust, the temperature is around 200 degrees Celsius, 400 degrees Fahrenheit, which is not that hot yet. This is the temperature of a kitchen oven. But 3,000 kilometers down, near the core, the temperature reaches 4,000 degrees in the lowest layers of the mantle. 4,000 degrees is hard to describe, it is still relatively cold compared with temperatures inside the Sun, for example, but it is sufficient to melt any man-made material. The most resistant high-performance ceramics that are used, for example, in the latest generation nuclear reactors to stop the reactor's core from falling down in case it would melt, can resist to temperatures up to around 2000 degrees, and the temperature at the lower level of the mantle is twice as high. At this temperature, any rock would melt immediately. But it doesn't mean the mantle is liquid though. It is actually rather solid, because something compensates for the heat, the pressure. Generally, a rise in temperature tends to turn a material from solid to liquid and then to gas. But pressure has the opposite effect. The rise in pressure forces materials to remain solid. We have all seen very liquid lava coming out of a volcano. It is liquid because it's hot, but also because pressure at the surface lets the rock be liquid. The same lava material, when it was in the mantle before rising to the surface, was kept much more solid, more viscous by pressure. This enormous pressure, which is called lithostatic pressure, goes up as you descend inside the mantle, and it counterbalances the heat to keep everything mostly solid. Mostly because it's not perfectly still. The upper layers of the mantle are liquid enough to allow tectonic plates to move. And the matter in the mantle also moves. Things can move because rocks at such high pressure are still able to very slowly deform, and because the center of the Earth is very hot, whereas the crust and the upper mantle are comparatively rather cold, and this creates a convection movement inside the mantle, this difference in temperature. That is to say, hotter material tends to go up towards the surface, and colder material tends to go down. This colder material comes from a large part from subduction between tectonic plates. When there is one passing under another one, its material descends into the mantle and is progressively absorbed by it. But this creates movements in this high pressure, high temperature environment. And on the other hand, where there is a rift between two plates and a new floor appears, the material comes from the mantle. It's a very slow process, but there is this constant exchange movement between the mantle and the crust. And sometimes this can be responsible for the presence of heavy materials close to the surface. For example, almost half accessible copper reserves in the world are located in Chile and Peru, near the Andes, and this is not a coincidence. These resources have been lifted close to the surface by convection in the mantle and tectonics. The mantle is also divided into various layers with different properties and different viscosities too. It is not homogeneous at all. Some parts are more viscous than others, but what we know about it is mainly based on theories, and the main observations that can be made are with seismic waves that are sent through the mantle. It is possible to guess what a layer is made of by studying how waves cross it, at what speed, how they are deflected, but exploring the mantle with a probe is extremely difficult because of the depth, the heat, and the pressure. There has been attempts to collect samples from the mantle or close to it by drilling on the seafloor where the crust is thinner. But these experiments have just scratched the surface and not reached further than the lowest levels of the crust. The various layers of the mantle end about 3,000 kilometers, 1,800 miles approximately, under the surface. Under this begins the core, but it is not homogeneous neither. There are two main regions of the core. First, there is a region called the outer core. Temperature rises again, up to almost 8,000 degrees this time, and so does the pressure, but not enough to keep the outer core solid. So it is believed to be liquid, and contrary to the mantle, it is no longer mainly rock, but metal this time, iron, nickel, and maybe traces of sulfur and oxygen. At the bottom of the outer core begins the inner core, which is our final destination, as it is the innermost layer of at the center of the Earth. But there is a lot to say about this system with the liquid and the solid core. There is no direct evidence about the composition of the core. All we know about it comes from information given when seismic waves cross it, and current theories about the formation of the Earth. The inner core is distinguished from the outer core, even though they have about the same composition, iron mainly. This is because the inner core becomes solid again. Pressure keeps increasing, and it counterbalances temperature at this depth, and we can figure out the inner core as a metal ball floating in the middle of a liquid metal ocean. It seems that the solid core is growing slightly at the expense of the liquid part, and this is because the planet keeps cooling down. As there is a little bit less heat year after year, but pressure remains the same, the part that is solid, the inner core, tends to grow at the expense of the liquid part. It's very slow, only 1 millimeter per year. But in geologic times, this is significant. It means 1 meter every 1,000 years, and 1 kilometer every million years. There are still several billion years to go at this rate before the liquid core disappears, but this should happen eventually, and the solidification of the entire core could have dramatic consequences for the entire planet. Because the core probably moves differently from the rest of the planet, as it is liquid and is not directly welded, attached to it. There is a theory that explains the existence of the Earth's magnetic field by the movement of the outer core. It is called the Dynamo Theory, and I'm going to explain you what it's about. Astronomers and physicists have detected quite a long time ago the existence of a magnetic field around certain bodies, including Earth. So what is a magnetic field exactly? You know magnets. They can pull some materials, metals, and they can repel other magnets. And with other materials like glass or plastic, they seem to not react at all. This happens because of the movement of electrons. You know that atoms are made of a core with protons and neutrons, and around this core, electrons, which are smaller particles. These electrons can move and circulate between atoms. This is what happens in electricity. Electricity is a flow of electrons between 2 points. Some materials, especially metals, are better at conducting electricity because their atomic structure lets their electrons move easily, lets them be separated from their atom. When we say we use electricity, what we do really is we create a bridge, a passage between 2 points that have different potentials. One can release electrons and the other is electrons hungry. And we use this flow of electrons to make a motor work, to heat something, or to transmit information in the case of electronics. Now, magnetism is another property related to electrons. Electrons are constantly moving, not only between atoms, but inside them too. They turn around the atom's core at high speed, and even more importantly, they spin like a spinning top. This spinning creates a force that can attract other atoms and turn each atom into a tiny magnet. Now, most of the time, this pull, this attraction at the atomic level doesn't extend to entire objects because atoms are put together a bit chaotically. They have different orientations and they are not organized in an orderly manner, meaning that the little pull generated by each atom is compensated by others, and as a whole, the object is not acting like a magnet. But sometimes materials naturally have this property and are natural magnets, or they can acquire it when they conduct electricity. When they conduct electricity, their atoms reorganize to pull in the same direction, and they become magnetic. For example, two wires conducting electricity in the same direction will attract each other, and they will repel each other if electricity moves in opposite directions. A few materials can have this property naturally, or they can acquire it when they are put in contact with another magnet that reorganizes the positioning of their atoms. These are called ferromagnetic materials, and they include elements like iron or nickel and alloys that contain them. This is typically how the magnet you may have on your fridge works. The area around such an object, where its attraction or repulsion is perceptible, is called the magnetic field. To obtain magnetic fields that are more powerful and can be used on demand, electromagnets have been created. They are used extensively in industry, and you may not know it, but you probably own several of them. They are used in motors, relays, loudspeakers, or hard drives. typical electromagnet is made of a core of ferromagnetic material surrounded with a spiral of wire. Electricity through the wire creates a magnetic field around the system, and the field disappears when the current is turned off. What an electromagnet does is basically transform electricity into magnetic energy, into magnetism. I am telling you all this because the entire planet we live on is surrounded by a giant magnetic field. And this magnetic field is a vital component to the equation that makes life as we know it viable on Earth. It shields the planet from radiations, from streams of particles emitted by the sun that would make at least human life unsustainable if they were to reach the surface. All around the planet, on the fringes of this magnetic field, there is a region of space of much higher radioactivity. It's called the Van Allen belt, where the Earth's magnetic field repels these particles. Since this magnetic field was discovered, that was more than a century ago, the question of why and how it works has been a field of investigation for scientists. The main theory that explains it nowadays is this Dynamo Theory. There are various practical possible explanations to it, but the concept is that the Earth itself generates constantly this magnetic field by transforming the currents of electrically charged particles that circulate between the core and the mantle into a giant natural magnetic field. This is possible only because liquid iron in the outer core can move independently from the mantle. Similar magnetic fields exist around other planets with a partially liquid iron core, like Mercury. Mercury is a small planet that could have cooled down quickly and lost its liquid metal core long ago if it was further from the Sun. But Mercury's core remains very hot, not really because of the Sun's heat that Mercury receives, but because of the Sun's pull. Mercury has an elliptical orbit around the Sun. This means that the gravitational pull from the Sun can be stronger when Mercury is close to the star, or weaker when it is farther. And these variations in the gravitational pull provoke frictions inside the planet. It is called tidal energy, and it keeps the core warmer. On the other hand, there are rocky planets with no dynamo effect and no magnetic field because they don't have enough of a metallic core, or it is no longer liquid. That's the case of Mars. Mars has no magnetosphere like Earth. Mars has a light atmosphere that absorbs some of the solar radiation, but still, the radiation level on its surface is about 60 times what it is on Earth, and even 3 to 4 times what astronauts absorb when they are aboard the International Space Station. This is one of the main challenges to colonize Mars, and an element, among others, that makes it very hostile to human life. For the time being, the only option for humans to survive on Mars would be to live underground or under anti-radiation domes. So, among all the elements that make life possible on our planet, including the atmosphere, liquid water, the temperature, the presence of basic bricks of organic compounds, the distance to the sun, there is also the very structure of the planet, and the fact that its core is not welded to the mantle, which makes the generation of this magnetic field possible. We have now reached the end of our adventure for tonight, but we now have to return to the surface, and to accompany you and lull you to sleep, I have compiled different soft music tracks from the YouTube library that can make you dream about the wonders of our planet, on the surface as well as under our feet. Sleep well, and I'll talk to you soon for another journey. Au revoir.